Hello, the few of you that are actually going to watch this video. I know most of you aren't going to watch this because you guys are lazy. Anyways, those people aren't you guys because you're actually watching this. So this is sections 9.3 and 9.4 in geometry, rotations and symmetry. These are the last set of notes we're going to go through before the final. So have your notes with you. Follow along. You can stop the video if you need to do an example. You can go back if you miss something. This is up to you. If you want to stop, you want to go faster. Hey, there's a double speed thing. You can make me talk really, really fast. Here we go. How do we draw and identify rotations of images? What are the different types of symmetry and how do we identify them? So, first let's tackle the idea of rotations. To describe a rotation, you need to know the center of rotation. It's going to be a point. The angle of rotation, which is how many degrees that thing rotated, and whether the rotation is clockwise, which goes in the direction of a clock, or counterclockwise, which is in the opposite direction. So a rotation is going to rotate around something called a center. It's going to basically pivot around it, and it's going to ask you how far does it go in terms of degrees, knowing that a full revolution is 360, halfway is 180, and which direction your rotation is going. Now, unless specified, all rotations are going to be counterclockwise because that's how math works. We go counterclockwise. We go this direction here. Alright, there are two rules for rotation. To rotate a figure x degrees about a point r. The image of r is itself. In other words, if you have a point on the point of rotation, the center of rotation, it's not going to move. It's basically like putting a stick, taking a sheet of paper and rotating it on that point. So that point, that corner is never going to move. Now, for any other point on that figure, V, let's call V, the distance is not going to change because it's basically going to be making a circle. So it's like imagine using a compass. So RV, the distance between R and V originally, is going to be the same. It's just pivoting around this point. And this is going to represent how many degrees the object rotated in terms of x degrees. So the image of the point of rotation, the center of rotation, is not going to change. A point that's not on the center is going to be the same distance away as the new point from the center, but it's going to move x degrees in one direction. So imagine this. Imagine drawing a triangle and that dot is in the middle of a circle. To rotate the triangle, you will place a pencil in the center of the circle and then spin the circle with the triangle around. If you move it clockwise, you get it like this. See? If you go 180 degrees from the last one, you see that it goes to it's like a reflection about the origin. Basically, you've rotated it halfway around. Now, let's go back to the original the triangle. You can rotate this however many degrees you want, either clockwise or counterclockwise. Here's 60 degrees counterclockwise, so it's going to come this way, like that. I had to rotate the whole picture because that's just how I had to do it. Alright, now, there are formulas for the rotations. We're going to do three different types of rotations. A 180 degree rotation, which basically means it's rotating halfway around, and then 90 and 270 degree rotations. Remember, all the numbers represent the counterclockwise direction. And we're going to have some translation rules, some motion rules. So to find the points of a figure that's rotated 180 degrees about the origin, change the positive negative sign of each coordinate. So the original xy becomes the new negative x, negative y. So all you're doing is flipping the sign of each coordinate. So notice here, on the original figure, this point here is 1, 4. Now, if you rotate it 180 degrees, you're basically moving it down to negative 1, negative 4. All you've done is switch the signs. That's a 180 degree rotation. For 90 degree rotations, we have another rule. Remember, we're going counterclockwise unless you're told otherwise. So you're going to move this one and rotate it this direction. So this triangle is going to end up in this quadrant, the second quadrant. So the rule for a 90 degree rotation, x, y becomes negative y, x. In other words, the original x now becomes the y. The original y, take the negative of that, and it becomes the new x. So if you take a look at 5, 5, the new point is going to be negative 5, 5. If you take a look at this point, 3, 1, 3 becomes negative 3, 1. In other words, the original y take the negative of that, it becomes the new x. The original x becomes the new y. Negative 5 comma 5, negative 1 comma 4. So again, notice the original x becomes the new y, x to x. The original y, 1, becomes negative and becomes the new x coordinate. So this is the rule. And if you graph it, you will notice that it rotates around the origin. For a 270-degree rotation, it's basically going 3/4 of the way around, or it's the same as just going 190-degree direction clockwise. The rule is x comma y, remember this is the original, which is this blue one, becomes y comma negative x. So you take the original x, negate it, make it the new y. You take the original y, keep it, and you make it the new x. So we have this green triangle, which represents the 270-degree rotation. The 1, 3 becomes 3, negative 1. The original x becomes negative and is the new y. The original y, 3, becomes the new first number, so 3, negative 1. So then 5, 5 is going to become 5, negative 5. The 4, 1 is going to be 1, negative 4. So these are the rules for 90-degree rotation and 270-degree rotation. Look at the original x and the y, do something to it, and those become the new ordered pair. Example 1. If triangle CAT is rotated 180 degrees about the origin, what are the coordinates of C', A', and T'? So first of all, we need the coordinates of C, A, and T. C happens to be at 2, 4, A is at 1, 1, T is at 6, 2. Now, if you remember what the motion rule is, how do we find C', A', T'? Well, you're going to use this rule, the one that's above you that you wrote on the paper. XY becomes negative x, negative y. So the 180-degree rule is pretty simple. You just take the negative or the opposite sign of each of the coordinates. So C' becomes negative 2, negative 4, A' becomes negative 1, negative 1, and T' becomes negative 6, negative 2. And if you were to plot that, it would be looking like this. C' there, A' there, T' there. So 180 degrees, again, all you do is switch the sign. Example 2. If now CAT is rotated 90 degrees, remember that's counterclockwise, so you're going to end up in here. What are the coordinates of C', A', and T'? Well, what motion rule are you going to use? Well, if you look at your paper, you can figure it out yourself. See if you can get the answer, pause the video, and try to answer it yourself. Yes, I'm not here to help you. Alright, so here's your motion rule. XY becomes negative YX. So you take your first coordinates. So if we look at C, the new rule is going to be negative 4, 2 for C. For A, it's going to be negative 1, 1. And for T, we're going to take the 2. We're going to take the 6, make it the new Y coordinate. We're going to take the 2, make it negative, and make it the new X coordinate. So 6, 2 becomes negative 2, 6. And there's your triangle there. C at negative 4, 2. A at negative 1, 1. T at negative 2, 6. This is a 90-degree rotation counterclockwise. Example 3. Now, if CAT is rotated 90 degrees clockwise, what are our answers going to get? Well, here's the motion rule. You can try it yourself if you want to pause the video. The rule is x, y becomes y, negative x. So C's new coordinates, C' is going to be 4, negative 2. A' is going to be 1, negative 1. T' is going to be 2, negative 6. So again, follow the rule, look at the coordinates, change it so that it reflects the new coordinates. And here's your 90-degree clockwise rotation. C' at 4, negative 2. A at 1, negative 1. T' at 2, negative 6. Finally, example 4. A four-sided figure of ABCD is rotated 180 degrees about the origin. What are the coordinates of the 4 new points? Go ahead and do this one. Well, the motion rule for 180 degrees is pretty simple. All you do is take xy and convert it to negative x, negative y. In other words, you just flip the signs for each one. So A is going to become negative 1, negative 2. B is going to be negative 2, negative 5. C' is negative 5, negative 1. And D' is negative 3, positive 1. And those are your answers. If you plot it, it looks like this: A prime, B prime, C prime, and D prime. So this looks like it's 180 degrees rotated around the origin. Number 5, if triangle ABC is rotated 90 degrees clockwise about the origin, what are the coordinates of A prime, B prime, C prime? Well, you've got the coordinates for A, B, and C. Give this one a shot as well. Alright, our rule is xy becomes y negative x. So A prime is 4, positive 1. B prime is 5, negative 3. C prime is negative 2, negative 2. So again, take a look at your original coordinate and apply this rule. So negative 1, 4 becomes 4, 4 positive 1. And there's your new triangle, rotated 90 degrees clockwise about the origin. Next, we're going to look at rotating regular polygons. So we have a regular pentagon, PENTA, and if you notice, you can divide it into 5 congruent triangles. So we're going to name the image of E if you rotate this 72 degrees, again counterclockwise, about X. So P is the image of E, because 72 degrees is 1/5 of the triangle. So if you rotate it 1/5 of the way around, P becomes the new E. In other words, when you rotate it, E is going to be where P is, where P started. So P is the image of E. Now, if you were to do a 216 degree rotation, that's basically 3 times around. So if you wanted the image of P for a rotation, you're basically going to advance 3 triangles. So the answer here is that P, we go 72 to A, 72 more to T, 72 to N, and N becomes the image of P. In other words, if you rotate P, N is where you're going to end up. Now, name the image of T for a 144 degree rotation about X. Give this one a shot yourself. Alright, we start at T. We're going to go 72 times 2 counterclockwise. So we go from T to N, and we go from N to E. And so E is the image of T. So the first thing you need to do is take 360 divided by how many sides you are, and then you have, and then you can figure out how many spots you're going to have to move. Now we're going to explore the idea of symmetry. A figure has symmetry if there is an isometry that maps the figure onto itself. For reflectional or line symmetry, one half of the figure is a reflection of its other half. So what you can do here is, if you look at one half of this mask, it's the same as the other half. Now what they say is about people that are attractive, that they have symmetrical faces. In other words, if you take one half of their face, cut the paper out, and attach the other half, it looks good. People that are not good looking do not have line symmetry in your face. If you want to try it with your face, send me a picture. I'll show you how ugly or pretty people think you might be. So we can look at also lines of symmetry. If you look at a hexagon has 6 lines of symmetry. Each one divides the hexagon into 2 identical halves. 1, 2, 3, 4, 5, 6. Alright? How many lines of symmetry does a rectangle have? In other words, how many ways can you cut the rectangle so you have exactly 2 of the same half? Well, you can cut it that way. You can cut it that way. It looks like you have 2 halves. But no, there's more. You can cut the diagonal. So you have 2 congruent triangles there, and you can do the other diagonal. So a rectangle has 4 lines of symmetry. Notice that a hexagon has 6 lines of symmetry. How do you think that's going to be? Notice on each line of symmetry, it goes to the center of the regular shape, or in this case, a rectangle. It's not even a regular shape. But notice the lines of symmetry always go through the center. Now, we have another type of symmetry called rotational symmetry. If a figure has rotational symmetry, it maps onto its own image for some rotation of 180 degrees or less. So take this equilateral triangle. Regular polygons all have rotational symmetry. If you rotate it, in this case 120 degrees, for a square 90 degrees, it's going to basically look exactly like it did when it started. To get those numbers, you divide 360 by however many sides the shape has. So if you have a hexagon, you divide 360 by 6. If you have an octagon, you divide it by 8. For an equilateral triangle, the angle of rotation is 120. In other words, if you rotate this triangle 120 degrees, you end up exactly with the same shape as you started with, looking exactly the same way. So one way to check this is to take your paper and rotate it. If you have a shape of rotational symmetry, you turn the paper, you put your pen in the middle of the shape, rotate it around. If it looks exactly the same without having to go more than halfway, you have rotational symmetry. So, example 6. Which of these have rotational symmetry? Now, this one, if you rotate it 90 degrees, you're going to end up exactly what you started with. So this has rotational symmetry for 90 degrees. This triangle, does it? No. If you actually rotated it, it would not look like it did when it started. What about this octagon? Well, it's a regular polygon, so the answer would be yes. And you only have to rotate it 45 degrees, because 45 is 360 divided by 8. Finally, there's the idea of point symmetry. A figure that has point symmetry has 180 degree rotational symmetry. In other words, if you rotate it 180 degrees, it looks exactly like it started. The equilateral triangle does not have rotated a point symmetry, because if you rotate it halfway around, it will not map onto itself. In other words, you cannot overlap it completely. However, many other shapes do, like squares, hexagons, octagons do. For point symmetry, just turn the figure upside down and it doesn't look the same as it started. It does not have point symmetry. If it does, it does. So hopefully you've watched the entire video or skimmed through parts of it. It's a good way to review if you missed something. You'll be doing homework problems in class tomorrow. If you didn't watch the video, well, too bad. The homework's still due during class, but you wouldn't hear this anyway.